Okay, before starting the lecture, please allow me to introduce Professor Koji Koyamada. Professor Koyamada is currently a professor at the Academic Center for Computing and Media Studies, Kyoto University, Japan. His research interests includes modeling and simulation and visualization. He is a member of the Science Council of Japan, a former president of the Visualization Society Japan, and the former president of Japan Society of Simulation Technology. He received the IMC Outstanding Paper Award in 1998, and the Visualization Society Japan Contribution Award in 2009, and the Outstanding Paper Award in 2010. He received his bachelor, master, and PhD degrees in electronic engineering from Kyoto University, Japan in 1983, 1985, and 1994, respectively, and worked for IBM Japan from 1985 to 1998. From 1998 to 2001, he was an associate professor at Evat Prefecture University, Japan. From 2001 to 2003, he was an associate professor at the Kyoto University, Japan. Let's warmly welcome Professor Koji Koyamada for his academic presentation. Today, the Professor Koyamada gave us the topic is visual analysis to support the derivation and the solution of PDEs using neural networks. Let's welcome Professor Koji Koyamada.
Thank you. Thank you for kind introduction. Can I share my slide? Okay. Yeah. Share. No share. We need to include audio. It's very important. Okay, sometimes I forgot including. So can I see my screen?
Yes.
Yeah. Okay. So
Yes.
thank you for this kind introduction. Today's my topic is about the visual analysis for supporting derivation solution PDEs using neural networks. My name is Koji Koyamada from Kyoto University. So I'm very pleased and honored to be given to this opportunity in this excellent international forum. Thank you. So it's about the 2 weeks before until the Beijing Olympics. It's a great event, I think. It reminded me Beijing Olympics in 2008. It's synchronized the starting year of the first visualization workshop in Beijing. So it's a memorial years, 2008 and 2022. The slogan of the Beijing 2020, according to the web page, together for the shared future. So very important message. Visualization can play very important role in achieving this slogan. And then I enjoy the several events in CSIG-VIS. So especially in 2019, I visited Chengdu, in which the several famous researcher in the city. So this is a snapshot of the conference hall, and then Arthur give a great speech in the whole. The chairperson of Yadong took me to the very interesting places, one of which is a Panda laboratory. At the moment, I have a great, had a great opportunity to meet very cute babies panda like this. And then very impressive event is about the phase changing opera in Chengdu. I'm very surprised at the speed in which the phase are changing in a minute, in a second. It's very impressed. So the CSIG-VIS aimed to improve the communication with visualization and the visualization analytics community in China and the surrounding region, include Japan. So I think it became a strong international conference because acceptance rate is 30%. It's a very strong conference, I think. So my talk today is about is composed of about the three topics. One is AI enhanced visualization, and then before the second topic, we a little bit describe about the surrogate model we are focusing on. So through the topic, I put a question: how does a research activity meet AI? So first topic is about the AI enhanced visualization. That's called as AI for Biz. In the topic, we introduce two projects. One is the 3D book data visualization. And then second project is we visualized plasma shape in a LHD type helical fusion reactor. Next, we describe about a little bit about the surrogate model, and then move on to the second topic, visualization enhanced AI, Biz for AI. So we introduced two projects. One is a PD derivation. Secondly, we'd like to describe the solution. So each topic accompanied by the short video, which describe constructed by our excellent students. I hope these students also attending this forum. Okay. So there are so many data points in a spatial temporal space because there are so many excellent technology of measure data in a spatial temporal space, drone and a telescope, and the smartphone also. It's a device in which we can measure the data set. So we categorize these point data into two. One is physical quantity measured at a certain spatial position at a certain fixed time. And then next category is about the data obtained at a certain spatial temporal. It's a more general form. Both spatial temporal data set can be processed by our technique. So as for the data visualization, we refer to this data flow or pipeline. Once we get a volume data set, which composed of the regular and then BFC and the irregular, we convert this volume data set into the geometry data, triangular and line segment points. Using computer graphics technology, we can render these geometry data into the nice, beautiful pictures. It's a data flow pipeline. Okay, so we are focused on the this spatial temporal data set, which is form of discrete. So for visualization, we need the continuous form of the data set. So we need some interpolation technique. To do this, first we generate a mesh geometry. In this case, we just generate triangular mesh. In this case, we make a reduction technique from 4 to 2. And then we locate a given point, in this case, red point. And then we calculate weights from outside 3 vertices. And then we can calculate interpolated value, simple expression like this. But this local interpolation cannot consider outside the triangle. In this case, 1, 2, 3, 4, 5, 6 points cannot be considered for the interpolation. To avoid this, to solve this problem, we explore some global expression technique. So we focus on neural network, especially fully connected neural network like this. So in this case, to construct the neural network model, the spatial temporal data set first fed into the input layer, in this case, X, Y, Z, T. Repeatedly by number of the number of points. And then the physical quantities define the points, in this case, U, that means unknown, connected to the output layer. And then we can define the mean square error predicted, and then input it. We employ some optimization technique to minimize this loss function. And then we get this kind of the neural network model, which composed of the layered form of the activation function. In this case, W mean the weights, sigma mean the activation function, like this, as you already know. So this is a neural network model that can be used for the global approximation for the spatial temporal space. This is a starting point of our talk. So this form of the function is based on a strong basement. It's a universal approximation theorem in the neural networks, which was presented by Svenko in the 1989. This is the abstract of the original paper. So it said that the representation approximates any continuous function of n real variables. This is a very important, strong message for the neural network model. So this basement applied to the various kind of the fields that is the AI application. So first, we need to visualize this neural network model. So how to visualize this neural network model? We think of the 3 approaches. Number 1 is to generate a regular grid. So first we prepare grids with adequate resolution like this. In this case, very small, 4 by 4 by 2, and evaluate the function value at each grid point. And then we got a regular volume data set, and we employ some scientific visualization technique, such as matching cubes or the volume rendering. Second approach is to render neural network model using particles. We sample the points in a spatial temporal space. And then we employ a particle-based volume rendering, which we developed previously. The third approach is very interesting. Ray trace the neural network model without grid, like this. For this approach, first we cast a ray in a spatial temporal space, and then integral brightness equation along the ray. In this topic, we focus mainly on the regular grid generation, but we describe a little bit about the approaches, the second approach and the third approach. So to generate a regular grid, the program is very simple. One example is like this. First, we prepare the large array, which named as the volume, and then we write down the simple code to put the value from the neural network model. Then we got regular volume. Then we apply, in this case, volume slice algorithm and isosurface algorithm like this. This is the basic simple approach. Second one is just use particle-based volume rendering approach. So let's show the short movie. This is the visualization of the simulation result, which is based on the particle or simulation technique. The result includes the particle, just a particle, not grid. So in this demonstration, we change opacity and then color mapping using interactive interface. But please note that they are just particle set. So if we assign opacity or color specific data, but at the data point there are unique distribution of the points, that is a particle density. So we need to some modification. This building represents the Fukushima power plant. The simulation itself is very interesting. But for us, it's a kind of the challenge in which can we implement volume rendering for particle data. That is a demonstration of our particle-based volume rendering. Thank you. So previously, we developed the particle-based volume rendering for grid data. It's very simple. First, we generate a set of opaque particles in each grid cell, and then project these particles onto the image plane, and then we use ensemble average, and then we got a smooth and semi-transparent images using opaque particle like this. But in this simulation result, we don't have grid data. So we need to develop a new technique, particle-based volume rendering for point data. Left side of the process represent the previous particle-based volume rendering. It uses this formula, the law, to estimate the particle density in a grid cell. And then we generate a particle. But PBVR for point data, we already have the particle in the simulation. But this distribution of the particle doesn't care of the visualization volume rendering. So we need to modification. So we derive this formula to modify the particle radius at the point. We just use opacity at the point to modify the radius of a particle. So we can use the same interface of the normal volume rendering for grid data. So it can be used also for neural network model, I think. So we move on to the first topic, AI for bits. So we can add this small box neural network model for the AI enhanced data visualization in this topic. First, we fed into the this geometry data, and then we got grid data. This is we think our AI enhanced data visualization. So we would like to show the two projects for this visualization. As a background, in recent years, research cases using CT scanning equipment have been published regarding decoding of ancient documents that cannot be opened. We are developing an analysis method digitalizing literature, assuming that the literature is a booklet. So in this case, research question is, how can we extract page information from three-dimensional booklet data? If we define a scalar field corresponding to the number of pages, and then generate the isosurface of the page, and map the booklet CT data on it, the question can be answered. So our proposal is described like this. In this method, we generate two types of volume data. One is three-dimensional image data from the scanned booklet, just like the human body. Yeah. And then we generate page volume data from the annotated points and the 3D image data. Diagram of our processes is like this. We can show overview of the.
In recent years, research cases using CT scanning equipment have been published regarding the decoding of ancient documents that cannot be opened. We are developing an analysis method for digitized literature, assuming that the literature is a booklet. In previous studies, we generated page volume data by solving the Laplace equation. Now, we used a deep learning network to generate the page volume data. We used two models for experiments, the MLP model and the PointNet-based model. By training these two deep learning models, the page volume data was successfully generated. Compared with the results of previous studies, it more accurately fits the real page. We used the generated page volume data to extract the page by data mapping. The results in 3 dimensions show that the text is clearer on the pages extracted by the deep learning method. The comparison result of extracting pages on 2 dimensions show that the deep learning method is more accurate. We define the accuracy to evaluate. By calculating the percentage of original page pixels in the extracted page, we can get the result as shown. In recent years,
Okay, we'd like to describe it in some more detail. So first, how can we digitize a booklet? In this case, we prepared the 7 printed paper like this. We regarded this set of paper as a simplified booklet. In each paper, we print some character like this. This booklet is put into this 3-dimensional CT devices. And then we got 3-dimensional image data. You can understand this curved line show the page cross section. And then we can count 1, 2, 3, 4, 5, 6, 7. This means that the paper, the number of paper is 7. The 7 pages small booklet in this case. So how can we annotate page number in the CT scanned document? We developed a web-based annotation tool like this. We visualize cross section of the CT image data, and then manual annotation can be made on the cross section of the image data. So the annotation and categorize the points into the 7 like this. So finally, we got the point data set, which categorized into the 7. You can see the 7 colored points in a 3-dimensional space. So next, how can we generate the page volume data from the point data? So we fed these point data into this neural network model. In this case, we don't include this t value, not time series. And then we got page volume data in which a scalar field is represent the page number. How can we represent page information on the page surface? It's like this. First, we apply merging cube technique to extract 7 isosurface page as a page. Then we apply a data mapping technique of the 3D image data onto the extracted isosurfaces. And then we get restored printed page like this. This is one of the results. For comparison, we construct Laplace equation model. The left column shows the Laplace equation result. This is the page cross section. Right figure show the ground truth. Apparently, neural network based approach can restore the page exactly, and then restore the character like this. This is the ground truth text. We use employed PointNet neural network. We'll describe later. So we employ 2 types of the neural network. One is neural network, general neural network, which is composed of the 4 layers. And then we also employ PointNet, which developed by the Stanford University groups. From comparative analysis of this, we can understand that the point net model outperforms the general neural network output with respect to the loss function value. Okay, move on to the next project, visualization of plasma shape and the LHD type helical fusion reactor. So what is a LHD? That means large helical devices. It's one of the world's largest helical devices with the surrounding coils that generate a strong magnetic field on a regular basis. In order to stably confine plasma in the magnetic field container, an infinitely calculating magnetic field line with no end is required to cross escape route for the particles. In addition, in order to create the donut-shaped cage with these lines of the magnetic force, it is necessary to add the twist like this, the lines of magnetic field. So this is the plasma region on the cross section of the LHD vacuum vessel. This pink region is named as the confinement region, in which plasma is confined by the cage of the magnetic field line. It is a core region important. And then outside this region, you can understand the green or blue region. It is called as the ergotic region. And then you can find this diverter leg, diverter plates. What does it mean, diverter? Diverter means the impurity which is closely related to the confinement. We need to eject the impurity of the plasma. And then this diverter plate need to catch them. This is the essential part for maintaining the plasma in this vacuum vessel. This is the background talk. So as another important background for the visualization, the visualization of the plasma region is indispensable for understanding the relationship with the fusion reactor's structure and then plasma regions for the maintenance of the fusion reactors. So in this case, research question is, how can we derive plasma region from a set of magnetic field lines? You can see this green curved line show the magnetic field lines calculated in advance for the visualization. So if we define a scalar field from the set of these magnetic field lines, the question can be answered. This is the extracted plasma regions in advance. And then this is the CAD model represented in the STL format, show the fusion reactor structures. Domain expert needed to focus on the interference of that structure and plasma regions. So our proposal is described like this. Using a neural network model, we would like to generate two types of volume data. One is confinement volume data, and the second is ergodic volume data. And then we apply matching cube technique to visualize plasma region data. This talk was accepted for the last China-VIS conference. So let's get started.
A magnetic field is used to confine the plasma to achieve controlled fusion. Because of the complicated distribution of magnetic field lines in 3D space, existing measures which are mostly based on 2D space are inefficient. We propose introducing the alpha-shape method and an AND technology. The Larmor radius was calculated at each point. Then, the coordinates of points with their labels, which indicates a point either from the plasma shape representation or the reactor model representation, were fed to an AND to pick up the overlapped regions. Under the Python programming environment, we use Google TensorFlow 2 to build the AND, and Mayavi to visualize the result. Here is the demonstration. In this reactor structure, the probability of having interference is shown in different colors. The warmer the color is, the higher the risk indicated. Meanwhile, we trace these highlighted areas back to their represented meshes, so that one can obtain detailed information using CAD editors.
Okay, let's describe it in more detail. So how to annotate magnetic field lines? We show the two categories, confinement and ergotic. Once we get a set of the magnetic field lines and then set up a cross section, and we use the same annotation tool as a 3D book visualization, and made the annotation which show the type of category. One is confinement, the another is ergotic. And then we have the point data with annotation. So we would like to describe some technical part of the automatic differentiation. So what is the automatic differentiation? It's a set of technique evaluate derivative of the function. In this case, plasma region existence probability function. This is realized by using a chain rule applied the layered propagate back using this chain formula. And then finally, we can get, for example, first order derivative like this. Please note that this is not a numerical approximation. This is the exact derivation of the given function. In this case, we are using this automatic differentiation for neural network models derivatives. So this is the schematic representation of a technique. First, we got a set of the annotated point from the magnetic field line. And these points fed into the neural network's input layer. And then we apply automatic differentiation to get the derivative of the plasma regions. So what does it mean? We just use a set of points which on the magnetic field line, but we also use the direction of the magnetic field line. So we made inner product of this derivative and this magnetic field flux direction B sub x, B sub y, B sub z. And then we have included information of the direction of the magnetic field line. So we calculate another mean square error. So we added, please, this RRE should be replaced with the IP. IP means the inner product. Thank you. And then we got a volume data set of the plasma region existence. And then we visualize plasma regions like this. This is the diverter lake. Clearly show the figure of the dipolar lake. Okay, next move on to the surrogate model, which is often used for the engineering and scientific computation. Especially in engineering simulation, engineering method has used surrogate model when the outcome of the interest, in many cases, the temperature or the pressure, stress is one outcome of the example. It cannot be easily measured or simulated. So simple model of the outcome is preferred. Most engineering design problem requires experiments and or simulations to evaluate design variable. So they need to construct surrogate model. So this is an example of a surrogate model using a neural network. Finite diameter models input, in many cases, boundary condition, the load condition, or geometry, etc. And then this neural network model, the output layer is connected to the outcome, that is the pressure, stress, or temperature. So this paper showed the good result of the surrogate model of the geometry and blood pressure. This model just output stress in 1 second. In the thermal management area, it has been called as a compact model. So in this figure, show the cross-section of the magnetic rotors. Engineers often focus on the temperature on the rotor surface. And then what kind of the factor made severe impact on the temperature? So they need to construct the compact or surrogate model of the temperature using these design parameters. This means the angle of the rotors, and then top fillet angle, top fillet radius, also top bottom fillet radius. They made several combination of the parameter, and then make a neural network model for their daily use. This is the example of the surrogate model. So feature of the surrogate model is the computer efficient. Instantly predict the analysis result using a neural network model. realizing an environment where you can enjoy the power of the numerical simulation at the design. This is what it means, the surrogate. And the freeform resource shortage by ultra high speed neural network calculation. But please keep in mind the physical consideration of the prediction result, which is not necessarily direct result connected to the physics. So the variety of the surrogate model is essentially important. So we think reference to the partial differential equation, it's closely related to the physics, is essential for the physical validity. So we started the PDE, Derivation of the Solution project. So as you already know, what are partial differential equations? It is a simple definition. It's a differential equation in which a known function is a function of the two or more variables, and then which includes the partial differential coefficient related to those of unknown functions. It is called the partial differential equation. A famous one is Poisson Laplace advection diffusion. It's an example of the partial differential equation. So they are often used in the field of the natural science to describe natural phenomena related to the field, fluid, gravitational field, and electromagnetic field. But we can think of the use of the social science and then humanity if we define some metric. We can derive of the solve the PDEs and the social sciences. So how do you connect this partial differential equation and the neural networks? We already know the answer. We can use of the automatic differentiation technique to derive to employ a partial differential terms. So how can we refer to the these PDEs? To answer this question, we introduce two types of the project. One is a PDE derivation and the PDE solution. So fortunately, I found a very nice framework which is developed by the NVIDIA modulus. It's a framework for developing the physics machine learning neural network model. And the feature, which is from the NVIDIA's website, novel neural network architecture and the design space exploration, optimized for the multi-physics problem, just for the constructing effective, efficient surrogate model. It's an example of the surrogate model of the thermal fluid dynamics areas. This is a thing which is installed on the chip, probably a GPU. So we think there are so many opportunities apply visualization technique to evaluate the several points. This is also an example of the scientific visualization application technique application. So next talk is about the visualization enhanced AI, in this case neural network, PD derivation. So explanatory models that use existing PDEs are very important for utilizing big data, which in this case mean the spatial temporal points from a variety of new phenomena, including new corona infection. Today, we have the 40,000 infections a day in Japan. So it's a very important topic, I think. So first we got measurement data like this, and then we will be able to have partial differential equation govern the data in the form of the this simple formula. This. So research questions: how can we derive PDEs from the discrete spatial temporal data? We propose that if we add the regularized regression error term, another term is this is a Russell regression or sparse regression, yeah, to the loss function, the question can be answered. This is the diagram of the proposed method. So to derive the partial differential equation, first we need to prepare measurement data, but currently we use pseudo measurement data, which is generated from exact FDM numerical simulation techniques solution of PDE. And then we prepare for the candidate of the partial differential terms. And then coefficient of the partial differential term are determined using a sparse regression. It's an answer to this question. So let's show the overview video.
First, we can see the information of data source and the neural network model configuration. Then click the display button. A parallel axis plot will be drawn. Information of the neural network type and its derivation error can be shown when hovering mouse on the line. Here we can select one of the top 10 structure and explore the results of data size by clicking the button. The green line is the derivation error and the blue line is the neural network model loss. X-axis is the data size, 20 scales from 100 to 20,000. Also, it is possible to highlight one of them. Here is the structure visualization. One circle represents 10 neurons. Then in the specific form of standard solution and experimental result. Then we can draw the slider to see the isosurfaces change by time. And zoom in, out and change view to see details. In the scatter plot, we can adjust the view to explore the plot. Here we can use slider to zoom in or out the candidate plot.
Okay, this is the end of the overview video.
First, we can.
Okay, we move on to the description in some detail. First, we construct a neural network model from the spatial temporal points. It's a kind of the pseudo measurement data generated by the FDM, FEM, also exact solution of the PDE. And then we got the neural network model, and then we define the mean square error. Then we apply auto differentiation technique to get a set of partial differential terms. In this case, we just calculate 7 types of the partial derivative terms. But in general, we need to extend the derivatives. And then we put the set of the spatial temporal points to formulate this matrix formula. So the number of the points is equal to the number of rows in this case. Each row represents the point. This epsilon means the quotient of the partial differential term. It represents the unknown in this problem. And then we can think of the regularized regression equation. We just add this term, regularized term. Epsilon means the quotient. So this is called the mean square error of the regularized regression equation, RRE. So we add this error term to the loss function of the neural network model. This can be regarded as the adequate training of the neural network model, which consider partial differential equation. And then we can view this process as a multi-objective optimization. In this case, objective function, two objective function. And then this type of the process is called, has been called as a physics-informed neural network, PINN. So I thought that this idea is original, but fortunately, unfortunately, in 2019, we found a Rice's paper, physics-informed neural networks. So currently, many researchers use this word, PINN. So we follow this trend, physics-informed neural network. So PD derivation system, the schematic displays like this. First, we put spatial temporal data, and then we get coefficient. But in this case, in the research stage, we think of the partial differential equation. So we can define this error metric, error sub epsilon. We know the exact value of the coefficient epsilon, and then predicted epsilon. So we can define a metric such like a norm. So what kind of the factor can be found to decrease this error is the important point in this research. So as a case study, we generate the training data from the exact solution of a PDE. And we made a random sampling to make spatial or temporal points. This black dot means the random sampling points. And then we use the uniform neural networks, which means that each layer have the same number of neurons. In this case, we 4 layers and 4 neurons. It's called the neural networks. And then number of layers changed from 1 to 5, and the number of neurons changed from 1 to 50. The first equation is a KDV. It's a famous equation with the exact solution. And then we calculate the coefficient. The bottom line is show the identified PDEs. You can see the similar formulation, similar coefficient like this, because we used minimum set of the partial differential terms, just like this. We just use 3 partial derivative. So it's a kind of the inverse problem. But we extend partial derivative terms to the several terms or non-linear term, and then we get this kind of the partial differential equation. With the viewpoint of the error metric, which described, is not good. But we may think that this is a new PDE created by the limitation of the boundary conditions. We think the PDE is independent of the boundary conditions, but in this case, we set a single boundary condition. So which derives a new PDE. Okay. And then error distribution can be defined in a 2D plane because we have the 2 dimension. One is the number of layers, and second one the number of neurons. 5 by 50. So what kind of the visualization technique can we use? It's a very simple heat map. But fortunately, Chinese researcher present a very similar result by changing number of layers and the number of neurons like this. But they present the very simple visualization result using just a bar chart like this. But the message is very important. We sometimes think that the increase of the number of layers, increase of the number of neurons can decrease the error. No, it's not so simple. Very complex distribution like this. So in this case, 5, number of layers 5, and number of neurons per layer or 50 show the local minima of the error. But they just show the loss function. We also show the PD derivation error. And then to the regular grid. We need to focus on the local minima. In the model of error, we can understand that 2 local minima. And then in the PD derivation error, we have just 1 local minima. The locations of local minima are different. It's important but a difficult message for us. In the general situation, we cannot assume PDE in advance. So we just see this neural network model error, but local minima location different like this. Next case study is about the advection diffusion equation. This equation also have the exact solution like this. So we conducted a partial differential derivation process, and then we get the identified PDE in the bottom line like this. Then we extend a partial differential library, and then we get a different type of the partial differential equation like this. So this also suggests that this is a new PDE created by the limitation boundary condition. It's a kind of the positive view, but to derive the PDE correctly, we need to prepare for the enough number of the boundary condition. So it's a kind of the problem. Error distribution in the 2D field is like this. In this visualization, we also focus on the local minima. It showed the same local minima location with both error, but another local error, local minima in the PD derivation error, the result of the neural network model error is contradictory. Yeah, it's also important suggestion. And another type of the case study conducted using a more general neural network, which means a different number of neurons are set up in each layer like this. In this case, 432 neurons in the layers. And then number of layers changed from 1 to 10. And the number of neurons changed from 1 to 512. So in this case, visualization viewpoint is very interesting. How can we visualize this high dimensional data? Because this error is defined on the 10-dimensional data. Each number of this row represent a number of layers. And then this show the number of neurons. And the 0 means the no layer after the sixth layer. So we use at this point parallel coordinates plot for this type of the visualization. In this case, we just 4 layer, and then each layer the intersection means the number of neurons. So in this case, this visualization said that the decreasing structure of the neural network can reach at the low errors. Rightmost axis represent the loss function. That is the error. So this is a very meaningful suggestion of the neural network structure. So finally, we would like to describe a PD solution project. So background of this project, as for PD solution, there are so many numerical simulation technique of the PDE, finite difference method, finite element method, particle-based simulation method. But they also think of the local interpolation to evaluate partial differential terms. So the use of the neural network model can employ local approximation features to the PD solution. So we implement the PD solution system. This is a schematic view of the system. First, we specify the PD like this. And then we use 2 types of the point data. One is boundary condition point. In the boundary condition point, physical quantity is associated with this point. Next type of the spatial temporal points, the no physical quantity are defined on the points. Just the coordinate of the point. These point sets are used to construct neural network model. Okay, so we have the two types of the point data, boundary condition, and then spatial temporal points. And then we construct physical informed neural network. So let's show the overview of our system. Sorry for the small region.
Thanks for your interest in our research. Here, we build an interactive system to visualizing the process of how to use physics-informed neural network to solve partial differential equations. The example here is 1D advection diffusion equation. The standard formula of the equation is shown here, with adjustable coefficients C and D. Another decisive factor are boundary conditions. For numerical solutions, the resolution in different dimensions could be set as important parameter, especially for the finite difference method used as a comparison. When we use PINN, its settable options include the structure of the neural network, the number of training samples in domain, on boundary and initial conditions, and also the learning rate and epochs. When all these parameters have been determined, you can press the Apply button. The backend system will quickly calculate the exact solution and FDM solution and visualize them. You can zoom in on them to check the details of the calculation results. After all epochs are over, the system will also output the result of the PINN. As the standard result, the exact solution will be compared with the results of FDM and PINN respectively, and the absolute error will be visualized. The average error and maximum error will also be displayed on the web page. The last picture shows how the train loss, test loss and test metric change during training. Thanks for your
Okay. Due to some system resource shortage, there are some noise or stops in the video. Sorry. So it's a little bit detailed explanation of the PD solution. First, we get a boundary condition point to construct the neural network model. And then we calculate derivative, just like a PD derivation. And then we put a spatial temporal point to calculate, evaluate a partial differential term. And then we just prepare the residuals. Please note that in this case, epsilon, which is a vector of the coefficient, is not variable. It's composed of the constant. So we also call it the physics-informed neural network. This is a schematic display of the PD solution like this. So it's a case study of the 1D advection diffusion equation. You can understand that this neural network-based model outperformed other traditional numerical simulation technique, FDM, FEM, in this case. So our system is composed like this. First, we set up the equation and then network structure, and then give a boundary condition, and then we get results, and then make a visualization using a heat map. This is an overview of our system. This system developed on the Streamlit library. It's a kind of the very common library in Python. So at this point, we can think of the requirement of the visual analytic system for the PD derivation and the solution. The first requirement is to qualify how much the point data and the constructed neural network model match spatial temporal space. The system already showed the animation of the isosurface. It's a type, the one visualization forms. The second one is how the diversity in the partial differential terms and the boundary condition decrease PD derivation error. I think it's a very essential requirement for the PD derivation. Requirement 3 is about the clarification of the how the neural network model parameter and the number of points decrease the PD derivation solution error. We already showed the error distribution in the hyperparameter space. We use parallel coordinate, and we also show the scatter plot in a 2D plot using dependent reduction technique. Also, we analyze the PD solution error, local global region. It's also an essential question. The difference between the local interpolation and the global approximation. So in the fifth requirement to clarify how to select partial differential term candidates, it's also an essential question using an EDM. So what is the EDM? We prepare the short video of this technique. Let's see.
An important approach to scientific inquiry across many disciplines is the use of observational time series data. The relationship between two time series can be depicted as a node-linked graph. We can construct the network by quantifying the relationships among time series. But the important question comes up with my mind. Is the relationship static? Or is it dynamic that changes over time? Because natural systems are often complex and dynamic, the relationship among the measured time series dynamically changes. So, it is important to integrate methods characterizing these dynamics with visualization techniques that can help to analyze the behavior of the system. We propose a visual analytics system to support the identification and interpretation of the system state from a dynamic graph. Here, we focus on empirical dynamic modeling. EDM as an emerging data science method that measures changing relationships between time series variables. EDM is used to construct a dynamic graph by time series data, and a snapshot of a dynamic graph is mapped to two-dimensional space by dimension reduction method. This 2D mapping plot and brush link visualization enable us to identify and interpret the system state. Our visual analytics tool enables to confirm the results of EDM analysis and a constructed dynamic graph. This view enables us to explore and identify the system state using the two-dimensional projection mapping. Identified system states are interpreted via brush link visualization. We integrated a novel data science method and visual analytics approaches to gain new insights into real-world systems.
Okay, this system for the extracting the system states and the visualize transition from the multidimensional time series data. If we regard the partial derivative terms the time series, multidimensional time series data, we can very interesting visualization result from the set of the candidate and the difference between the states. It's a near future project, I think. So in summary, visualization data science meets AI through the physically informed network, which is based on the universal function approximation and then auto differentiation. And the application exam, we show the 4 type of the project. And then in future, I would like to think of the rendering of the neural network model, which is similar to the implicit function visualization. Thank you.
Okay, thank you very much for this wonderful
Thank
talk.
you.
I see some problems mentioned to me 3 years ago have been solved very well. Great progress have been made. It's amazing. We now receive some questions. Maybe the first question is, what are the boundary conditions required in the treatment of non-layer PDEs? Can you say the question?
Okay, thank you. It's a depend on the PDE. So, for example, thermal fluid phenomena, we can think of the inlet flow or outlet flow in some specific region, or the specify the temperature at some region we can think of. Is that your question? Answer your question?
Yeah, I have another question. Another question is the point cloud data has a lot of noise, missing the points and the external points. How to use the appropriate method to improve the accuracy and the rendering effect in the data pre-processing stage?
Okay, thank you for a very interesting and difficult question. There are so many denoising algorithms. First, we need to explore. And then we would like to have some smoothing filter for the removing the noise. But it depends on the situation of application, I think. It's a case by case. Thank you.
Okay. Today, maybe you can stop here. This session, we can stop here today. Today, the Professor Koji Koyamada gave us an impressive speech. For our audience, if you want to get more information about the previous lecture or look at today's lecture, please visit the website of CSIG-VIS. Thank you for the participation. Thanks again to Professor Koji Koyamada.
Thank you. Thank you for interesting discussion.
Okay, thank you. Okay. This and the next time on the February 10th, 2022, we will have the CSIG-VIS International Lecture Series. The title of the lecture is Immersive Analytics in the Connected World. The invited speaker is Tim Weaver, who is the former Monash University, Australia. Okay, we look forward to see you again. So thank you very much for the participation.